Today's video is sponsored by Omaze. Stay tuned for a word from them at the end. The deep sea is a realm of curiosities. Throughout history, our nightmares have been fueled by tales brought back by seafarers of giant monsters from the depths and leviathans larger than life. But in the last few decades, deep sea exploration has uncovered a place of wonder, conflict, and beauty. A hidden world alive with the coruscating dance of bioluminescence, concealing vibrant reefs and towering cities, supporting communities of organisms in ways that challenge and progress our understanding of life. And although there may be no Lovecraftian horrors lurking in our oceans, it may be true that the deeper you go, the stranger and crucially larger its inhabitants appear. The tendency of deep-sea creatures to grow to sizes far exceeding those of their shallow water counterparts is known as deep-sea gigantism, and it is a phenomenon best exemplified by the invertebrates of this dark and peculiar world. From isopods that exceed 40 centimeters in length to enormous cephalopods. It is a trend that seems illogical for an ecosystem characterized by low food availability and scarcity of prey, where you might expect a larger body to hinder survival. In this film, we'll delve into the research that might help to explain this observation and take a look at some of the giants that rule the depths. When it comes to considering the harsh conditions of the deep sea, there is a common misconception that pressure poses a challenge to the animals that reside here. According to NOAA, for every 10 meters or 33 feet you descend, the pressure increases by 1 atmosphere. This means that the bottom of the ocean's twilight zone, 1,000 meters down, sits at around 101 atmospheres of pressure. And yet, life here appears unfazed. Transparent creatures, cast adrift in the endless gloom, like this siphonophore, a colony organism comprising hundreds of tiny animals called zooids working together to survive. The largest of these siphonophores is able to grow longer than a blue whale. Even approaching the ocean's deepest point, the Challenger Deep, more than 10,900 meters down, there is life. The deepest known fish, the Mariana snailfish, is able to survive at a depth of 8,000 meters, where water pressure is 801 times greater than at the surface. Pressure isn't much of an issue for these creatures that are themselves, for the most part, made of water. In fact, the buoyancy of ocean life means they don't have to work against gravity, and it is this that allows many of them to grow to such immense sizes without collapsing under their own weight. This explains how creatures of the deep are able to become so huge, but in order to find out why they do, we need to delve into their biology. Their immense growth has been explained in general terms by two laws, known as Kleiber's rule and Bergmann's rule, both of which have attracted significant criticism within the scientific community. Kleiber's rule proposed that animals that are larger will tend to be more efficient. A whale, for example, having a mass hundreds of times that of a small fish, will have a metabolism that is significantly slower. This is due to the nature of blood vessels and the circulatory system of animals. As body volume increases, the surface area increases more slowly, so larger animals have smaller surface area to volume ratios, and less energy per gram is lost through heat, requiring less replacement energy per gram. A slower metabolic rate is a huge advantage for animals in the deep sea, due to the scarcity of food down here. Below 200 meters, at the mesopelagic zone, light from the sun fades to a dim haze. This gloom is insufficient to support photosynthesizers like plants, algae, and phytoplankton. With no primary production taking place, the entire food web of deep midwaters must instead rely on scraps of food that sink from the more productive surface waters. A continuous trickle of organic particles known as marine snow, comprising dead material and feces. Food is scarce, so energy must be conserved, incentivizing deep-sea animals to grow to larger sizes in order to become more efficient. Take the amphipods, for example. These crustacean scavengers are found in every part of the ocean, from beach hoppers hiding away in seaweed on the shore, to 10,911 meters down in the furthest depths of the Mariana Trench. Here, the hadal amphipod takes to the unlit stage, even possessing enzymes that are able to digest wood. They can, and do, consume just about anything that falls to the sea floor, filling an important ecological function by recycling nutrients from even hard-to-digest material back into the environment. Without them, the seabed would vanish beneath a deluge of dead plant and animal material. These crustaceans can consume detritus at a rate between 60% and 100% of their body weight each day, for they are highly adapted to this task. Their legs have pincers with a movable half and a sharp edge used for tearing off pieces of food. At over 34 centimeters long in the hadal zone of the ocean, the species Alicella gigantea is a slow-moving scavenger which has been observed clumsily stumbling into bait, latching on and gorging itself for hours. But although it is far larger than shallow relatives, its size is not so odd when we consider it has evolved to fulfill a niche that, in shallower water, is occupied by other large bottom dwellers like crabs. One of the most common illustrations of deep-sea gigantism is the colossal squid, a 700-kilogram, 15-meter-long creature which dwells 2.1 kilometers below the surface. It is not only the largest invertebrate on Earth, but also has the largest eyes of any animal. But despite its size, very few have ever been observed, let alone filmed in the wild. Red devils, or Humboldt squid, may reach 2.5 meters in length, and are the largest of the so-called flying squids. And below, suspended at depths of around 4,000 meters, an even bigger cephalopod. At 8 meters long, and with slender arms and tentacles held perpendicular to the body, the Magnapinna or Bigfin squid appears as if it's holding a marionette puppet. These long tentacles drape into deeper waters and probe for zooplankton, allowing the squid's body to remain concealed in the dark above as it feeds. Almost nothing is known about the bigfin squid. It was first sighted only 20 years ago, and has been captured on film just a handful of times. This is footage of the most recent sighting, captured by one of NOAA's remotely operated vehicles, on the 9th of November last year, nearly 2.5 kilometers down in the Gulf of Mexico.
What is that? Ooh! Ooh, a squid! Ooh,
yes, a squid.
Ooh, follow it. Look how cool.
I know, it's just so...
It's a bigfin squid,
it's
maybe?
ghostly.
Magnapinna?
Magnapinna?
Oh man, look at him.
Although deep-sea gigantism tends to affect invertebrates more than any other animal group, it may also explain the morphology of some of the depth's vertebrate residents. Lurking in the cold polar depths of the Arctic Ocean, one of the largest sharks can be found in the gloom. This is a Greenland shark, belonging to a family of deep-water sharks called sleeper sharks. Growing to nearly 7 meters long at depths of over 2,000 meters, they have evolved to enhance their efficiency in a number of ways. A distinction can be made between their structural mass and growth mass. Structural mass, which contributes to internal and external body structures of an animal, requires energy to be used up for maintenance. Reserve mass, however, does not. Growing larger also allows animals to store more food in their reserve mass, and therefore travel greater distances without needing to eat so regularly. The reserve mass of sleeper sharks is immense, with some Greenland sharks weighing in at up to 1,400 kilograms, compared to shallow water sharks like this mako that may weigh between 60 and 400 kilograms. Living up to their name, sleeper sharks are one of the slowest moving sharks in the ocean, cruising along at 0.3 meters per second. Comparing it again with the short-fin mako, the sleeper's caudal fin is shorter and broader, and not suited to continuous high-speed cruising. Instead, it is suited to rapid bursts of acceleration for capturing faster prey, while conserving energy between meals. But these sharks tend not to waste energy on active hunting techniques if they can help it. Instead, they scavenge, led by their sensitive sense of smell to large food falls like this baleen whale carcass. Here, they will gorge themselves and store large amounts of food in their capacious stomachs. One study into a 3.7 meter long female sleeper shark from Trinidad, California, revealed its stomach contents had a mass of 136 kilograms. Such immense food stores means large animals can cover greater distances when searching for food or locating a mate. It allows them to rely on nutrient-rich hotspots like the whale falls, without starving during the long journeys between them. And what's truly remarkable is that the greatly slowed metabolic rates of these sharks means their lifespans are dramatically extended. When scientists experimented on the lens tissue of 28 female Greenland sharks from the North Atlantic, using radiocarbon dating on the innermost layer of the lens, they estimated the two biggest sharks to be around 335 to 392 years old. But Kleiber's rule does not explain why animals that lack a digestive system, or are sessile and waste very little energy on movement, can still exhibit gigantism. The sponge grounds of the ocean depths are populated by thousands of animals that demonstrate this. This sponge, measuring 3.5 meters long and 2.1 meters tall, was found at a depth of 2,134 meters, near the Hawaiian Islands in 2015. It is the size of a minivan, and like most denizens of the deep, it survives on marine snow. In the case of this and other deep-sea sponges, its large size may simply be due to a lack of disturbance from waves or typical sponge predators like turtles. A second theory that might explain the phenomenon of deep-sea gigantism is Bergmann's rule, which proposes that sea animals tend to increase in body size, with a decrease in temperature. It is consistent with the observation that most sea animals that exhibit gigantism are found in colder regions. In the deep sea, the lack of sunlight causes temperatures to plummet. This leads to increased cell size and lifespans, as well as a slowing of metabolic rates. In fact, the phenomenon of gigantism is most prevalent at the Arctic and southern oceans, where even in the shallow waters, animals like sea stars, sponges, basket stars, and worms all grow to enormous sizes compared to their warm water counterparts. For well over a century, zoologists and explorers to the poles have recorded their observations from dredging creatures from the depths, including sea spiders the size of dinner plates, with leg spans of 60 centimeters. In other parts of the ocean, the same species of sea spider grows no larger than 1 millimeter. Two-meter-tall giant sponges cling to drop stones, large boulders that fall from passing icebergs, providing islands of rocky habitat on the soft mud for filter feeders to cling to. Thanks to them, feather stars and cold-water corals have colonized the region. Well adapted to a stable and unchanging environment, these plant-like animals grow very slowly, but to enormous sizes. Very few fish are found here. Unlike most marine ecosystems where they dominate the food web, fish struggle to survive the freezing temperatures. Instead, the Antarctic deep is a seemingly prehistoric world, dominated by the giant invertebrates. Creatures here belong to a community that has been isolated from the rest of the planet for millions of years. The powerful Antarctic circumpolar current swirls around the frozen continent, creating a steep temperature gradient that stops marine animals from spreading. Their isolation has led to the diversity we see today, and the conditions of this cold underwater world has led to the enormous sizes they demonstrate. A slowed metabolism means many polar inhabitants can be described as living in relative slow motion, extending their lives. Crucially, warm water holds less dissolved oxygen than cold water, because the faster-moving molecules allow oxygen to escape more readily. So, the icy waters at the poles are remarkably oxygen-rich. But while low temperatures increase oxygen availability, they also reduce metabolic demand for oxygen due to the slowing metabolic rates, and this creates a far larger ratio of oxygen supply to demand. This releases cold water organisms from oxygen-based constraints on body size that inhibit the growth of animals in the tropics. In other words, they can sustain larger bodies without needing to worry about not accessing sufficient oxygen to maintain them. This is the oxygen temperature hypothesis, and it may underlie another phenomenon called polar gigantism. But if this is indeed the case, then polar giants may be particularly susceptible to warming temperatures, offsetting the fragile balance of their environment. Climate change is occurring at faster rates at the poles than anywhere else on Earth. As the ice melts and sea temperatures rise, the once oxygen-rich waters of the poles become depleted, and large-bodied organisms can no longer sustain their metabolic processes. And on top of that, their fragile, once isolated ecosystem has already seen an influx of invasive marine life. King crabs, voracious predators that had been kept at bay by the constraints of the polar front, expand their range as polar seas grow warmer. And here they devastate the sea floor. They gorge themselves on animals that never needed to evolve to defend themselves against such predators. Examining the ecology of oceanic islands may hold the key to understanding polar and deep-sea gigantism. Islands are isolated from other landmasses, and so they tend to develop indigenous biodiversity through diversification of the organisms that arrived there. Over time, they transform to form new species that display an astonishing variety of traits to survive and thrive in their new home. Isolation drives speciation. This process, in which organisms diversify rapidly from ancestral species, is called adaptive radiation. On islands, it arises from the unique resources available, and the new biotic interactions that in turn open new niches. The only way to survive in these unfamiliar worlds is to adapt quickly. In the Galapagos Islands, 13 species of small land birds, called Darwin's finches, are a classic example of adaptive radiation. Their common ancestor arrived on the Galapagos about 2 million years ago. Since then, they have diversified into 15 new species, each different in body size, beak shape, song, and feeding behavior. With so little competition to hinder their evolution, the finches were able to exploit numerous different lifestyles, or niches. Thus, islands create a scale model of evolution. But due to limited resources, competitors, and predators, the diversification of island fauna often follows an ecogeographical rule. In 1964, mammalogist J. Bristol Foster compared 116 island species with their mainland relatives, and observed that many island inhabitants evolved larger body sizes, called insular gigantism, while others became smaller, called insular dwarfism. His explanation was that the smaller animals get larger when predation pressure is reduced due to the absence of predators on many islands, and typically larger animals become smaller when food resources are limited on islands. In 1973, evolutionary biologist Leigh Van Valen formulated a rule based on Foster's study. This became known as the island rule. This is demonstrated by creatures like the enormous Galapagos tortoise, which has been isolated for 3 million years, is endemic to these islands, and is the largest living tortoise species on the planet. In 2006, a study led by biologist Craig R. McLean examined the gradient from the shallows to the depths, using this same framework of terrestrial islands. They found that the deep sea may be functionally similar to an island. In a fashion that seems to mirror the island rule, the deep sea also has limited resources, limited predators, and is isolated from the rest of the ocean. As a result, there was diversification in the depths too, following a mass extinction event that occurred during the Cenozoic period 65 million years ago. Shallow water creatures ventured deeper after the event and diversified into deep sea fauna. McLean et al. Observed that many deep sea taxa do indeed follow the island rule, such as gastropod mollusks. One of the tiniest gastropods, belonging to the genus Dentimago, dwells in the deep sea, and exhibits insular dwarfism in a similar manner to that observed on islands. But in addition, many deep-sea crustaceans, like the giant isopod, grow enormous compared to their relatives that rarely exceed an inch or two in shallow waters. Down here, they can grow to 40 centimeters in length and weigh approximately 1.7 kilograms. These examples suggest that overall trends in body size for deep-sea animals are a result of reduced resources available in this environment. They will tend to converge on an optimal size for their particular ecological strategy and habitat. But unlike islands where limited resources selects for smaller body sizes, the opposite is true for the deep sea, as animals are not confined to a limited spatial range, and so can travel larger distances in search of food, thus requiring larger bodies to sustain them on these journeys. It's also been suggested that there is simply an evolutionary opening for larger body sizes in the deep sea, perhaps caused by the absence of many predators capable of feeding on larger organisms. For example, one of the only known predators of the 13-meter-long giant squid is the sperm whale, which must venture down into the depths from the surface to feed on them. Or perhaps the need for animals to conserve energy simply means an active hunting lifestyle is less favourable. Overall, deep-sea gigantism demonstrates the role of natural selection in driving evolution and survival. particularly for an environment characterized by challenging conditions and limited resources. Evolution tends towards the most effective adaptations to grant animals the best chances of survival. And whether large or small, evolution selects for the best adapted body size to survive these conditions. Though widely debated and often controversial, the research that has been done into the science behind deep-sea gigantism has significant implications in the human world. It is believed that climate change may have a greater impact on ocean dwellers than any other population of animals. As the colder oceans warm up, the balance of temperature, oxygen supply, and what organisms are present will throw the equilibrium off course. And the giants, which rely so heavily on this fine balance, may be the first to go. This portion of the video is sponsored by Omaze, which has a sweepstake on right now where you have a chance to win a Tesla Model S Apex, an electric car that can do 0 to 60 in under 2 seconds with a range of 396 miles. And even if you don't win, you can help support the Peterson Automotive Museum, a non-profit that explores and presents the history of the automobile. Your donation can help the museum extend its education programs, as well as aid the museum in developing new exhibitions, community events, and funding programs such as Yellow Brick, a free program for teens and young adults interested in attending trade school. So, for your chance to win a custom Tesla Model S Apex and support a great cause, the Peterson Automotive Museum, head to omaze.com/naturalworldfacts and enter now. The experience closes on January 27th at 11:59 p.m. PST. Thanks for watching.